Hi everyone, my name is Karen Heeter and I'm coming to you from the University of Idaho in the United States. And today I'm going to be talking to you about my experience using blue intensity within the field of dendroclimatology, specifically for creating temperature reconstructions across the contiguous United States. And I'm sorry I couldn't be there in person today, but I will have my email at the end. If you have any questions or anything you'd like to discuss further, please feel free to get in contact with me, and I look forward to it. Just a brief outline of today's talk. I want to start with an introduction where I just speak a little bit about temperature proxies from tree rings, specifically in North America, kind of the current state of what's been done and where we are now. And this also applies to the use of blue intensity within North America to date. And then the real bulk of the talk will just be my experience with kind of the methodical procedures of going through BI on new species, in different locations. And then I want to give you two major examples of projects I've been working on, both in the eastern and western United States. And then finally, I'll wrap up with my current and future work with BI in North America. As I'm sure many of us are aware, tree rings are exceptional sources of paleo-environmental data because they can provide accurately dated proxy information at the annual resolution. Well, based on the principle of limiting factor, we're able to attain paleo temperature information from trees growing in temperature-limited environments. And in North America, trees whose radial or densiometric growth that is predominantly limited by temperature can be found both at the high latitudes or the high elevation locations at lower latitudes. So in North America, tree ring temperature records are primarily derived from conifer species and using ring width, maximum latewood density, otherwise known as MXD, or more recently, blue intensity, or BI. The application of X-ray based techniques such as MXD were hugely important for developing a network of temperature-sensitive tree ring records for North America. And this is exemplified by the vast MXD network developed by Briffa and Schweingruber in the 1980s. But moving forward to present times, we have another exceptional temperature-sensitive tree ring network, the N-trend network, yet substantial spatial gaps in the coverage of these records still exist. And so this is where I started thinking about how new tree ring metrics such as BI could potentially be used to fill the spatial and temporal gaps in the coverage of temperature proxy records for North America. Before I begin talking about my experimentation with BI, I briefly want to walk you through the reasoning and a quick history behind experimenting with visible light techniques. Although MXD data work really well for dendroclimatology, it's fairly expensive and time-consuming to produce. So throughout the last several decades, we've seen an increase in research looking to provide alternative tree ring parameters to MXD that respond similarly to temperature variation, but that are based on visible light techniques instead of the more expensive X-ray based techniques. And so the scanned image on the right is an Engelmann spruce core. And I just want to focus on the year 1954 and just really want to look at the latewood portion of the ring. So here we can see that the latewood is comprised of cell wall and lumen area. And Unosky and Robinov 1986 find that using high-resolution scan images, latewood brightness, or the amount of reflected light, was associated with the ratio of cell wall to lumen area. And their work is later expanded upon by Park and Teluski 1993, who find that maximum latewood density is strongly positively related to cell wall area. Then we have the pioneering work by Shepard et al. 1996, who later find that both latewood density and latewood brightness are correlated with April and May average temperatures. And then finally, in 2002, McCarroll et al. Are able to show that minimum blue reflectance is strongly negatively correlated with maximum latewood density, and if inverted, can actually act as a surrogate parameter for MXD. So this is really the first application of what we know today as blue intensity. For my dissertation research, I was interested in experimenting with and applying blue intensity methods on high elevation conifers across low to mid latitudes of the United States for the purposes of dendroclimatology. With this work, I aimed to examine BI metrics themselves, as well as the relationship between BI and other tree ring metrics, and BI and climate variables. Ultimately, as you will see in the following slides, I was able to use BI to reconstruct summer temperature variability back through time across multiple regions of the United States. For those of you who may not be super familiar with BI methods, there's a lot of work that must be done before the data collection actually begins. And this work is related to the quality of the wood image. And the thought being that because BI relies on visible light images, the quality of the data is directly related to the quality of the image that you provide. So prior to my work, the only work with BI in North America was done using spruce, or the genus Picea, which is typically really light and even colored across the wood. So for the many new species I wanted to work with, there were drastic discoloration issues between the heartwood and the sapwood that really required attention. So I worked with both chemical treatments and the use of the delta BI metric to see if either method could be used to correct any color bias resulting from the heartwood-sapwood discoloration. I also applied differential chemical-based resin extraction experiments to quantify what the presence of these non-mobile wood compounds does to the BI data itself. I was also interested in tackling issues related to imperfections in the wood, such as the presence of resin ducts, and whether these were true resin ducts, such as those commonly seen in the genus Pinus, or rows of traumatic resin ducts, such as those commonly seen in the Picea or Larix genera. Now, ultimately, the presence of resin ducts did adversely affect the BI data, but because resin ducts could not be chemically extracted like the resin content itself that you saw in the previous slide, they had to be dealt with using the ring delineation software Recorder. Discoloration due to fungal staining and natural weathering also needed to be addressed. Like many places in the Northern Hemisphere with long, diverse settlement histories, sometimes old living trees, which could be used to extend the tree ring record back over the past millennium, were hard to find in certain regions of the United States. And thus, I relied on remnant or cultural sources of wood material as my sources of paleoclimate information. So here are some of the examples of the discoloration I commonly saw in my samples. All in all, the majority of new species I worked with required some type of chemical treatment prior to BI data collection, the most common being ethanol-based resin extraction. And another common treatment to remove blue fungal staining from Engelmann spruce involved hydrogen peroxide-based bleaching. And while there are certainly many examples of where the delta BI metric can be used to remedy discoloration issues, chemical treatment and the use of the latewood blue metric seem to provide better solutions for certain genera, such as Pseudotsuga, which you see here on the left image. Besides sample treatment, my examination of BI also involved looking into how and where the data were collected for each sample. For my BI collection, I used an Epson 12000 XL scanner with Silverfast calibration software to acquire the wood images, but then all the ring data were collected using the software Recorder. So for BI, we're typically only interested in the blue wavelets of the visible spectrum. But modern scanner technology, which is an additive color, also allows us to collect red and green wavelets in addition to just the blue. And so part of my examination of new species and color intensity data looked into how the red and green channels were related to data from the blue channel and the differences in their subsequent climate responses. And I will say that the BI data always produced the more robust temperature proxy data compared to the red and green channels for the species I was looking at, and probably warrants further examination. I'll now share a few examples of how I've applied BI methods for dendroclimatology in the United States, first starting with the eastern US. I first want to point you back to the work I previously mentioned by Shepard et al. 1996, who found that latewood brightness using red spruce could be used to provide temperature proxy data for the eastern US. And I was interested in expanding upon this work by applying BI to a low latitude population of red spruce and seeing how my results would compare. I developed BI and total ring width chronologies and examined the temperature response of each chronology. The delta BI metric was ultimately used because of discoloration issues in the red spruce cores. But I found that the delta BI metric had a positive association with September-October maximum temperatures, where there were no time-stable significant relationships between total ring width and maximum temperatures. And we were pleasantly surprised at how well the BI data responded to temperature, but ultimately we're not that surprised that the ring width didn't respond very well. Comparable responses to this study using MXD and ring width have been shown in the lower latitudes of the US, especially in the western US. But additionally, the spatial nature of the relationship between the delta BI chronology and the gridded temperature data were very promising. And since that early work, my colleagues and I have been working to develop a network of temperature-sensitive chronologies using BI from both red spruce and eastern hemlock in order to provide multi-century estimates of summer temperature variability for the entire eastern United States. The majority of my dissertation involved building a network of BI chronologies across the western US. This work is still ongoing, but today I'll show you some results from a portion of the network across the Rocky Mountain region that's developed from late wood blue intensity of Engelmann spruce. Here is a breakdown of the 26 high elevation Engelmann spruce sites across the Rocky Mountain region of the United States. For each site, I developed both total ring width and late wood blue chronologies. The latitudinal range of the network spans 33 to 49 degrees north, and many of these sample sites were previously sampled for the Briffa and Schweingruber MXD network. For each site, I first evaluated the relationships between local temperature variables, both mean and max temperatures, and both total ring width and late wood blue chronologies. Across the entire network of the sites, the strongest, most temporally stable relationships occurred between the late wood blue chronologies and maximum temperature. The strongest response occurred in the month of August. And in comparison to their late wood blue site counterparts, the ring width chronologies typically did not show strong responses to temperature. Across the network, there were substantial differences in the relationships between radial and densiometric tree growth at each site. This was evident by the instances where ring width chronologies did show significant responses to growing season temperatures and were highly correlated with their late wood blue site counterpart chronologies. While future work to better understand the relationship between radial and densiometric growth across the network is ongoing, we did find that even the temperature-sensitive ring width chronologies did not have as pure of a temperature signal as the late wood blue counterpart chronologies. In the arid western U.S., this pattern is likely attributable to the competing influence of hydroclimate variability on radial growth of Engelmann spruce in this region. Using a cluster analysis, all temperature-sensitive late wood blue chronologies were grouped into 4 regions, and we assessed regional temperature response of each late wood blue chronology. We found the strongest positive regional responses to current year maximum temperatures. Through a series of regression experiments, we identified the optimum seasonal target for each regional reconstruction. Using a nested principal components regression technique, we used late wood blue chronologies to develop 4 regional maximum temperature reconstructions for the western U.S. Reconstruction models are strongly representative of temperature variability for each respective region across space and through time. With these regional temperature reconstructions, we are able to characterize unprecedented warm season maximum temperatures of the last 2 decades in the context of the last several centuries. These reconstructions allow for the comparison of spatial patterns of temperature variability through time and provide insight into the relationships between temperature and other climate variables influencing environmental change across the western United States. Additionally, these BI-based temperature reconstructions allow for comparisons with other temperature proxy records from from across North America to better understand patterns of internal variability, as well as the relationships between tree ring proxy records themselves. Unsurprisingly, our BI reconstructions are very similar to those produced by the Briffa and Schweingruber over their common period. Notably, the overall similarity among the BI and MXT records in the Western U.S. points to the realized value of using BI methods to provide updates to extensive pre-existing temperature proxy networks in a timely and cost-effective fashion. We also can use these BI records to address issues of both spatial and seasonal representation in the Northern Hemispheric ensemble temperature records. As I wrap up today's talk, I hope that my experiences with BI were informative and inspire you to experiment with these types of methods in the future. I'd say the main takeaways from my dissertation work are as follows. First, blue intensity is an effective tree ring parameter for reconstructing temperature, especially in places where traditional tree ring width may not always work. But as such, blue intensity methods are very much still in their infancy, and we need to recognize the current limitations to continually progress the science. For example, what could blue intensity measurements tell us about hydroclimate variability in other places in the world? And then secondly, networks are important for characterizing regional patterns of historic climate variability, and they should not be forgotten. And third, improvements are still needed to the northern and the southern hemispheric temperature-sensitive tree ring networks. And perhaps BI is an important addition to solving some of the spatial gaps in coverage of these networks. So on to some current and future work. As of January 2022, the global tree ring blue intensity network is comprised of over 230 BI chronologies, with 221 of these chronologies representing the Northern Hemisphere, and with 185 chronologies being developed and published within the last 4 years. My current and ongoing research emphasizes the utility of BI methods on conifers at decreasing latitudes in North America by targeting tree ring collections derived from high elevation locations. Using a similar approach, many other recent studies have also emphasized increasing the latitudinal extent southward of the temperature-sensitive tree ring network by targeting collections from mountainous environments. But despite major spatial improvements over the last decade, obvious spatial gaps still occur in the Northern Hemisphere paleotemperature record. And aside from New Zealand, the Southern Hemisphere is virtually devoid of temperature-sensitive tree ring records. And I very much look forward to future efforts by the tree ring community to remedy this issue. And lastly, I am currently working to develop a paleotemperature atlas for North America based on MXD, ring width, and blue intensity chronologies. So far, so good, but there's still a lot of work to be done, so stay tuned for more. So thank you again for listening to my talk. I hope you found it informative. If you have any questions about anything I covered today, feel free to email me at kheeter@uidaho.edu. Thanks, and I hope you guys have a great rest of your workshop.